You might think building software is just getting the first version out the door, but the reality is that most time and budget are spent long after release, during maintenance. Requirements change, and your initial design will be tested. This initial duck pond architecture uses a clean, top-level duck superclass for shared behaviors like quacking and swimming. By branching down, subclasses like the mallard and redhead ducks inherit these methods while handling their own unique displays. It looks like a logical hierarchy, but rigid structures only stay efficient until the exact moment a client asks for a major new feature. 6 months after launch, the executives decide the simulation needs an upgrade. The ducks need to fly. The intuitive developer move is to add a fly method right into the top-level duck superclass. But putting that behavior at the top of the tree pushes it down to every single subclass. Looking at the bottom of the hierarchy, we realize we just forced the inanimate rubber duck to take flight. A single localized update created non-local side effects. To prevent inanimate objects from flying, we could remove the behavior from the superclass and force specific subclasses to implement a new flyable interface. But Java interfaces don't contain implementation code. If 48 different ducks fly the exact same way, you now have to write and maintain that exact same flight logic in 48 different places. This destroys code reuse and creates a massive duplicate code problem. Strict inheritance forces inappropriate behaviors on subclasses, while broad interfaces create maintenance nightmares. Neither approach effectively manages a behavior that changes across some, but not all parts of a system. To fix this, we apply our first foundational object-oriented principle: identify the aspects of your application that vary and separate them from what stays the same. We take the varying fly and quack behaviors and physically pull them out of the main hierarchy to isolate them. Next, we program to an interface, not an implementation. We establish a fly behavior interface and build out concrete classes below it, like flying with wings or squeaking instead of quacking. But if the behavior is completely separated from the core duck class, how do we connect them so a duck knows which flight style to use when the program runs? By giving the duck class a reference to the behavior it needs, we avoid the side effects of inheritance while still allowing different ducks to share the same flight logic. This has a relationship, allows us to favor composition over inheritance. Looking at the code block inside the duck class, the duck holds a variable referencing the behavior interface. When it needs to move, it delegates the work to that behavior object. Because it relies on an interface, we can use a simple setter method to swap out the entire flight algorithm dynamically at runtime. By encapsulating the specific behavior and delegating it through composition, you isolate the changing parts of your code. You can now alter algorithms on the fly without touching your existing client code. You've rebuilt the simulation using the strategy pattern. It defines a family of algorithms, encapsulates each one independently, and makes them interchangeable from the client's perspective. The structure relies on 3 pillars: encapsulating variance, favoring composition, and programming to interfaces. Design patterns provide a shared vocabulary that allows teams to communicate complex architectures instantly. When you tell a team member you're using a strategy pattern, they immediately understand the structural design and its constraints, without needing a walkthrough of the implementation details. Loading your brain with these patterns changes how you approach problems. Instead of getting bogged down in individual classes and methods, you start solving problems at the architectural level.